This is a sum of 4.5 about quantitative data. So what is it? Well, it's used to quantify a problem by generating numerical data into usable statistics. It's used to generalize results to a larger population and can be recorded by different collection techniques such as surveys and questionnaires. Some of the benefits are that they can compare results to normative data. You can compare between different populations. You can make predictions on sports performance. You can compare different kinds of sports performers, and you can identify trends in different health. So there are 4 different ways of organising data. These are using range, creating an order rank distribution, a simple frequency distribution, and a grouped frequency distribution. So the first way is range. The range is the numerical value distance between the highest number in a set of data and the lowest number. The way to work it out is by simply subtracting the lowest value from the highest. From the table to the right here, you can see that the group of gymnasts have taken part in a sit and reach test, and their scores have been recorded. The range for this set of data would be found by identifying the highest score, which is 65 centimetres, and the lowest score, which is 44, and therefore 44 from 65 is 21. This therefore means that the range for this set of data is 21 centimetres. The next way of organising data is by using an order rank distribution. This is when a researcher, for example, goes back over the data collected, in my case, the female British gymnast standing vertical jump scores, and ranks them from the highest value to the lowest value. This can only be used, however, when the number of participants is less than or equal to 20. Therefore, the data I've displayed in these tables to the right are efficient, as there are only 8 participants. Any more than 20 would make it a very long process for any researcher to rank them all. The third way of organising data is by using the simple frequency distribution. In this way of organising data, the cumulative frequency must be worked out. This is a running total of all the frequencies. You tend to use simple frequency distribution when the number of participants is less than 20 and the range is less than or equal to 20. The idea of it is to have 2 main columns, one for all the individual raw data scores and the frequency scores in the other column, as you can see from this table here. You can also have other columns, for example, a column that shows the number of scores as a tally and the cumulative frequency. The frequency column is the number of times a specific score was achieved. And so the last way of organising data is by using grouped frequency data. This is when group intervals are calculated by the range divided by 15. In this sort of data, one column has the raw data groups of scores and the other has the frequency of scores. Unlike the simple frequency distribution, this way of organising data is used if the number of participants is greater than 20 and the range is greater than 21. And finally, there should ideally be groups of scores. However, it can differ between 0 and 20. Right, so now we move on to ways of presenting data. The different ways are going to be discussed in this video, and these are line graphs, scatter graphs, bar graphs, and histograms. So the first way of presenting data is by using a line graph. This is my example of a line graph down here, which shows the relationship or correlation between the scores of 14 participants taking part in the flying and static sprint. The idea of the line graph is to display change over time as a series of data points connected by straight line segments on 2 axes. Just as my graph does, line graphs determine relationships between 2 sets of values. The last aspect of them is that the independent variable, which is what you can change, is on the horizontal axes, and the dependent variable, which is the one you measure, is on the vertical axes. So relating back to my graph, the independent variable, or the variable that is changed or manipulated, is the participants that ran, and the dependent variable, or the variable that's measured, is the time it took them to run that specific distance. The second way of presenting data is with a scatter graph. These also display relationships, but between 2 quantitative variables plotted along 2 axes. Again, my example is down here, and this graph shows the correlation between the participants' upper arm girth and their chest throw. Just as the line graph, the independent variable is on the horizontal axis and the dependent variable is on the vertical. In my graph's case, the independent variable is the participants again and their upper arm girth. Then the variable we measure is how far they can throw the ball off their chest. In these graphs, there can be a line of best fit to represent the trend. And then finally, they visualize the strength of the relationship shown. Another way of presenting data is by using a bar graph. Once again, my graph example is down here, and this one shows the correlation of skin fold on participants' biceps and triceps. Bar graphs display the quantities of qualitative or categorical data. Now, an example of this could be age group or religious affiliation. The idea behind bar graphs is to plot the number of times a particular value or category occurs in a dataset. These types of graphs can be displayed horizontally or vertically, and in my graph, it's displayed vertically. The last way to present data is by using a histogram. These are a graphical way of presenting a frequency distribution of quantitative data. They can be used to plot frequency of scores, percentages, or proportions. They contain what's called an interval range. This is selected to reduce the amount of information while still providing enough variability to picture the shape of the distribution. The most important factor about these types of graphs is that they are created when the data is continuous, thus there are no gaps between the bars, and histograms can be used to display a normal distribution curve, which I'll go on to talk about now. Okay, so this is the distribution curve. In this example to the right, as I just mentioned, the normal distribution curve is over a histogram, which is usually where they come from. The most common pattern is the bell-shaped curve, and in this, the scores in the data are as likely to occur on one side of the average as the other. Throughout the data, the central tendencies, which are the median, mode, and mean, are all equal. Then finally, the number under the normal curve is always equal to 1. Normal distributions are actually denser in the centre and less dense in the tails, and 68% of the area of a normal distribution is within one standard deviation of the mean. Now we move on to skew diagrams, but this will be quite brief. So skew diagrams are typically used when the data set isn't normally distributed. Skews that have extreme values towards a positive end have tails that point towards that end, and these are positive skews. However, if the presence of the extreme values are the negative of the distribution, they will have the point but towards the negative skews. Now also briefly we have the outliers. So outliers are data points that appear to be significantly different than the majority of the data points. They can be identified by using the outlier labeling rule. One way to solve having an outlier is by using the Hawkins technique called trimming, in which you remove the data points from the analysis that are unlike most data in the set. So for example, in this data set, 21 is the outlier. So to solve this, the researcher would just exclude it from their results. Another way of solving the issue is by using the technique in which legitimate outliers are modified to become the next nearest acceptable value. So again, using this example, instead of trimming out the outlier 21, the researcher would make it the next highest number, which is 9.